I'm very happy to have Jeff Dean here giving a talk. He's at Google now. He actually got his PhD from this fine institution in '96, I believe. He was my first PhD student. So he then went on to work at DEC Western Research Lab and did a lot of cool stuff there, including the digital continuous profiling infrastructure, very cool system. And then went on to Google and has done a lot of cool things there, and he will tell us about them.
Thanks. Thanks, Greg. So welcome, everyone. I'm very happy to be here, and I'm going to give you a little bit of a flavor of the kinds of things that we work on at Google, and give you a picture kind of behind the scenes. You know, lots of people use Google and they type searches into boxes and they get results back, but I want to give you kind of a flavor of the kinds of things that happen when you type your query in, and some of the other kinds of things we're working on in our systems infrastructure and new products. So let's see. I'm going to focus mainly on what are the kinds of interesting problems that crop up when you try to organize a large amount of information, as our web search does, and some of the systems infrastructure underneath the covers. And then I'll focus on what kinds of interesting things can you do when you have lots of data, like lots of web pages and so on, and lots of computational resources. What kinds of things does that enable? And then I'll talk a little bit about our engineering organization, which is a little more chaotic than you might think. And then I'll conclude. OK, so I'm not really much for mission statements, but Google has one. And I actually like it a lot, because it sort of hints at what we're trying to do, which is not just provide search over a bunch of web pages, but to take lots of other kinds of information that exists in the world and make it accessible and useful to people. We started to branch out from just doing web search with products like Gmail, Google News, these kinds of things. And we've actually introduced a thing to search printed books by scanning them and OCRing them. Those are kind of some of the flavors that are implied by this mission statement. And I think it's not a bad one. It also means that we'll never run out of work to do, and almost anything fits under it. So what more can you ask? OK. So a lot of the work that we do is sort of dealing with issues of scale. So I'd like to give you just a sense of that. So Google has an index right now of about 4 billion web pages. And if you think about the average web page, it's about 10 kilobytes of data. And we want to provide search over that. In addition to just the amount of data that we're searching, we're handling a very large query volume, so lots and lots of queries per second. And that also is sort of another sense of scale. So it is a big problem, but it's reasonably solvable. You'll need a lot of computers and disks. And on top of that, you need to put interesting networking and interesting software to deal with all these machines and all this data. One thing I'd like to get across in this talk is that dealing with scale actually comes about in a huge range of areas in computer science at Google. So from the lowest level area of hardware and networking, what kind of basic computing infrastructure should we have that will let us deal with the scale of data we're trying to deal with? Then in distributed systems, how can you build really reliable systems out of unreliable components? And then algorithms and data structures, the complexity of the algorithms you choose when n is 4 billion matter a lot. So you really have to be careful about choosing the correct algorithms for dealing with lots of data. Whereas if you're just trying to sort 10 numbers, it doesn't matter so much what kind of algorithm you choose. And then there's a lot of interesting areas in machine learning and information retrieval that how can you analyze lots and lots of data in order to improve the quality of search results? You do a query for something fairly broad, like cats or something, and there's 10 million pages that match. What kinds of other interesting data can you process in order to separate out what are the interesting pages about cats from pages that happen to just mention cats in passing? And here's an area where I don't think we've actually done very much, but is an interesting area for future exploration in dealing with scale, is user interfaces. Basically, when you do a query like cats and you get back 10 million results, it would be interesting to provide sort of new and interesting ways of navigating those sets of results and refining your query that more than just typing in a few more words into your query or deleting a few words. And I think we haven't really done very much in that area, but I expect to see sort of interesting directions in the future in that, rather than just showing a list of 10 results. OK, so one thing that we've made a decision about is that we tend to build on very low-cost commodity machines because, well, this slide sort of illustrates why. Basically, we want to get the most computational power per dollar that we can, because the more computational resources we can get access to, the larger the index we can search, the more expensive the ranking algorithms we can consider, and so on. So here's a simple comparison of a fairly high-end Intel server. It's an 8-processor machine from IBM. Has 8 2 gigahertz Xeons and 64 gigabytes of memory and 8 terabytes of disk, and it's $750,000. Very nice machine. It has really good memory bandwidth, has really good communication speeds between the processors, and so on. On the other hand, from racksaver.com, you can get a rack of 88 machines, each of which has 2 comparable speed Xeons and has 2 gigabytes of memory. So, and roughly the same amount of disk. So basically, for a third the price, you can get something with 22 times the CPU, 3 times the memory, and the same disk. That's why we use commodity PCs. On the other hand, the IBM system has some nice features like redundant power supply. So if the power supply goes out, well, it'll continue to work. On the other hand, this thing probably has 88 power supplies. OK. So Google was started by our 2 founders as a research project at Stanford in roughly 1997. And at that time, they were trying to get computational resources to explore their ideas about using the web graph structure as an interesting way in doing search. And so the way they acquired machines was they would go to the loading dock. Their advisors apparently weren't giving them machines. So they would go to the loading dock, and they would offer to set up machines that other research groups had ordered. And then they would kind of keep them for a couple extra weeks and use them, kind of survive on the float of other research projects, machine arrivals. It did mean their cluster was pretty heterogeneous. And then over time, Google was formed as a company, and we started to build machines ourselves out of individual components. So this is basically the initial design, such as it is. And we've learned a lot over time. For example, this machine has a shared power supply for 4 motherboards on each of these trays. And there's you see the 4 reset switches there for each of the machines, and the Ethernet cables going in. There's actually 2 machines kind of behind the front 2, and the Ethernet cables kind of go in between in the side of the rack. And there isn't tremendous airflow in this design. And there's also a thin layer of cork between the motherboards and the metal tray. But we eventually realized that perhaps cork was not a really integral part of computer architecture. And we moved on to more traditional designs that have all the connectors on the front. They have just Ethernet and power, basically. You plug those in. At this time, this was during a very big expansion in the data center industry. And data centers were basically, hosting providers were charging by the square foot, which is an interesting business model, given that their costs are mostly derived from power consumption and cooling. You kind of don't give the users of your space the right incentives. And so our incentive was to cram as many machines as we could into each square foot. We did help them out with the cooling a little bit by buying our own fans. You also tend to get quite good at moving out of bankrupt data center providers areas with this approach, as you can see by this picture, and moving into new ones. So another area of scale is being able to sort of manage large amounts of machines efficiently and sort of be able to set up large clusters quickly without too much fuss. And so this is a new data center we're moving into in 2001, and 3 days later, it's all wired up. Basically, all these machines are on, the racks are on wheels. They're all sort of pre-wired within the rack. So you wheel them in, you lock the wheels down. Earthquakes, you don't want them rolling around too much. And then you wire up the switches on each rack into a central switch for the whole cluster, and presto, you have a cluster. So that's kind of where we are today. OK, but if you have that many machines, you really have to worry about failure because if you think about your average desktop computer, it's probably going to fail once every 2-3 years or something. But if you have 1,000 of those, that means you're going to have at least one machine failing every day. And that's just sort of what you would expect. And so you have to deal with failures in software. You don't really want to be running around every day trying to fix the one machine. You can't have anything in your software that depends critically on this one machine being up. Or at least you try to avoid that as much as you can. So you basically, one nice property of dealing with failures in software is that for capacity purposes, in order to handle our query volume, you actually need to make multiple replicas of each interesting server anyway. And so by making 6 copies of something for capacity reasons, if you lose one of them, well, your capacity is diminished a little bit, but you also have redundancy already in place because of the replication. And it's also easier because a lot of the applications we deal with are mostly read-only data. Relative to how often we update the index, we handle many, many, many queries per day or per second. So I think one of the nice things about our application is it's very easy to parallelize. And it's mostly read-only, so that means that you are able to use kind of slightly less than robust hardware and deal with failures in software. So let's think about an example of how you can use this cluster of machines in an interesting way to build a reliable service out of these unreliable parts. So think about our current Google index, which has 4 billion web documents plus a bunch of other kinds of documents. It's basically the same kind of thing you would see in the back of a book, where you have, for each word, the list of documents and positions within those documents where those words occur. And you get a query like, I don't know, University of Washington. You want to find pages that have University and of and Washington. And so you walk along these lists that tell you where the words occur. And you find documents that have all 3 words. And you have positional data to help you order the search results by finding documents that tend to have those clustered together, for example, or in bigger fonts. So obviously, this index is too large for one machine. So we have this thing called PageRank that we compute, which is basically a query-independent measure of how important we believe a page is. And this is derived through an iterative computation on the graph structure of the web. Basically, if lots of people point to a page, that's a sign that it's more important. And if lots of important people point to a page, that's a sign that it's even more important. So one thing you can do is when you want to structure the index, you need to split it into pieces anyway. So you can use PageRank as a total order on these pages. And so you split it into a bunch of pieces. We call those shards after the image of breaking glass. But it's basically just partitioning the documents into pieces. And then you basically are going to take these shards, which are each a small collection of documents. And so each one of these is going to be like a mini index of just those documents. You're going to send the query to that index, and it's going to find search results for that piece. And other pieces will do the same thing. Then we can replicate these shards. And if we want, we can make more replicas of pages that we believe are more important. So that if we lose a machine, we'll have more replicas of the more important pages than the less important ones. And then you do the same thing for the actual documents. And we also replicate this whole structure both within a data center, where we have a lot of machines, and across data centers, because we have multiple data centers, because for 2 reasons. One is we want to be able to tolerate, say, loss of connectivity to a particular data center. Like if a backhoe goes in and cuts fiber to the data center, we want to still have another data center where we can serve traffic. And the other thing is we want to have data centers close to where our users are, and users are spread out all over the world. So the speed of light actually affects the latency with which users can get our search results. And so you want to be close to users on the West Coast, users on the East Coast, users in Europe, users in Asia, and so on. Because we found that if you make your search fast, people will tend to use it more. It's a very different feel if your search returns in half a second than if it returns in 3 seconds, because if it returns in half a second, it feels much more interactive. You're able to refine your query, do those kinds of things that allow people to sort of interact in a better way. OK, so just as a review, here's a search results page. So these are the search results that we're going to find in our index. One thing that Google does is we make money by serving advertisements that are sort of distinguished from the search results by saying sponsored links, and they're off on another part of the page, so people know which things are sort of generated by our algorithms and are not affected by monetary issues, and things where people were being paid. I think that distinction is very good for users because if you allow yourself to take money for putting things in your index or affecting your search result ranking, you're basically becoming very biased towards things. And so this has been a good way of doing things for us. OK, so once you type in this query, let's see what happens. So the query comes into a data center. We use DNS to load balance across different data centers. So we'll stick a user at a particular data center for a little while. And then this is kind of a view of one data center that is set up to serve our web traffic. We actually have many different web servers. So there's a front-end load balancing system that takes care of routing that query to a particular web server that's going to handle your query. So the query comes in, and the first thing we do is we want to find out what results we're going to show. And to do that, we're going to search our index. So this is over here. So remember, I said we split the index into pieces, right? These things called shards. And then we make multiple replicas of each shard for both for capacity and fault tolerance. So in order to do the query, we pick one of the replicas from each shard. We send the query to each one. They each search over their local index, given the query, to find the best scoring documents in their shard. And then they sort the results and send back the top few that are the best ones in their particular shard. The web server then merges these results, sorts them, and decides what are the best 10 across all the shards. In parallel with that, it's also sending the query off to the ad server, to the spell checking system, and a few other servers to get information about other kinds of things we want to put on the search results page. Once we've decided on the 10 results we're going to show to the user, what we have are just sort of numeric identifiers that we assign to each document plus scores. And we actually now have to go get something meaningful for users, like the title and a little summary of the documents, sort of a snippet from the document. One thing about Google's search results is that our summaries are query specific. So when we decide to show you 10 documents, we go fetch the contents of those documents and look through the document contents in order to find regions of the document that are sort of densely populated with your query terms, or relevant, we believe, are relevant to your query terms. So the summaries, often you can tell from the summary alone, this is a good document for my query or this is not. And it allows people to sort of visually skip over things. Whereas if we just chose sort of the first 50 words of the document as our summary, that generally wouldn't work so well. So we decided the 10 documents. We sent it off to the doc shards. Doc shards are similarly replicated. And we get the results back, and then we put it all together and send it back out the top as the HTML page to the user. And this all happens pretty fast, in like a quarter of a second, typically. And there's roughly 1,000 machines involved in this process. And in parallel with your query, the data center is also processing many and many other queries at the same time. OK. So that's sort of a flavor of what happens when you type a query into Google. What I'm going to talk about now is some of the infrastructure that we've built over the past few years to address some of the needs that we have in terms of both storing large amounts of data and processing data efficiently, and making it easy to build large-scale data processing systems. So the first thing I'm going to talk about is a solution that we've built in-house for storing data. We basically want to use the disks on all our machines to store data. I'm not going to talk so much about our work queue system, which is basically a job scheduling system. So if you have a job that you want to run on a bunch of machines, you can submit a job, and it sort of takes care of looking for free machines on a cluster of machines and scheduling them. And then I'll talk about a system called MapReduce, which is designed to help simplify a lot of kinds of processing that we want to do. OK, so the Google file system. This system is designed to do two things. One is to store data reliably, even in the presence of unreliable machines. So if we lose a machine, we want to not lose the data that that machine was storing. And the way to do that is replication. It's a little trickier because this data is mutable. But basically, every piece of data is stored in multiple machines. And we tend to try to spread the copies of the machines out across single points of failure. So we, for example, don't want to store all the copies on the same rack because that shares a central switch that is a single point of failure. If that switch failed, you wouldn't be able to get to any of the machines on the rack. So we spread the data copies out across racks, for example. And we have a master that is responsible for all the metadata in the file system, basically the file names. And it keeps track of which chunk servers are the other part of the file system, which are basically all the machines and raw disks and a little server to manage reading and writing the data to the disks. So the master manages metadata and keeps track of chunk locations, but all the data transfer is done directly from the clients to the chunk servers. So what this means is that you can have a lot of bandwidth into this machine, into this file system, because you have maybe several thousand chunk servers, all with their own network interfaces, and maybe you have several thousand clients that are all writing in or reading from the file system. You can end up getting a lot of a very high transfer rate. Okay. And we found this system to actually address our needs fairly well in terms of storage. Oh, one thing I wanted to say about this slide. Another alternative to replicating data across machines would be to use RAIDed disks on, say, an individual chunk server. The problem with that is, first of all, RAIDed disks are more expensive, and we don't like to pay a lot of money for our machines. The second thing is, even if the disks underneath are rated and provide redundancy so that if you have a disk head failure, if that machine fails, you still can't have access to your data. So the data may be still around, but you can't access it until someone actually physically goes and replaces that machine. And so that's why we tend to spread the data out by doing replication across machines rather than having an underlying rated file system or something that would do that. So we have a paper about GFS if you're interested that you can access there. It was published in SOSP last year. And so basically, this system is able to sustain fairly high read and write loads of like multiple gigabytes per second in the presence of hardware failure. So as hardware fails, the master is responsible for making more copies of chunks that have less than the desired number of copies. And that's kind of all happening in the background. You typically don't notice unless you lose a lot of machines all of a sudden. And then you'll notice a big flurry of re-replication of chunks. So here's kind of a picture of our basic computing infrastructure in one of our clusters that we use for development. So we have basically the GFS master, which is a single machine with a couple of replicas for failover. We have a bunch of machines in the cluster that serve as chunk servers. And this is our scheduling system that is responsible for doing sort of large-scale job scheduling on these machines. And there's a little kind of daemon that helps out the scheduling system running on each machine. And then you have a bunch of jobs running on those machines. Some of them take a lot of memory and resources, and the work queue master takes care of considering that when it schedules other machines, other tasks. OK. So even if you have some of these things, it's still the case that it's pretty difficult to write sort of fault-tolerant computations that can process lots of data, and you want to use lots of computational resources. You want to run a job on 1,000 machines because you want to process so much data that if you ran it on one machine, it would take forever to finish. But you don't really want to write lots of fault-tolerant code in the particular application you're trying to write. You'd like it if that was sort of taken care of for you. So one of the things we found is that lots of our problems amount to processing a lot of input data in order to compute some derived data from that input data. Like we process documents and we compute an index from it. Or we process our web logs and we find out how many queries we got from each country in the day or whatever. We'd like a framework that provides the ability to do sort of automatic parallelization and distribution of computations across a big cluster of machines without the user code having to be really complicated and messy. We'd like it if the library would provide fault tolerance and would schedule I/O so that it's efficient. We'd like to use the disks and the network efficiently. And it'd be nice if we could provide status and monitoring. So a system we've been building over the last year or so is called MapReduce. Basically, it takes its inspiration from the Lisp functional operations map and reduce. And we realized that a lot of the problems we're trying to solve could be handled in this framework, where basically you write a map function that takes an input key value pair and produces a set of intermediate key value pairs where the key space doesn't necessarily have to be the same. So for example, you might have the input data be a URL as the key and the contents of those URLs that we've crawled as the values. And you just want to count, how many pages do we have from each host on the web. So the map function will just process the URL, parse out the host name, and emit the key value pair hostname, 1. Then the reduce function is going to take an intermediate key and all the intermediate values for that key and combine them in some way. In this case, it's just going to simply sum them. So a particular host name and then all the values, which are all 1, it's going to sum them all up and give you host name 4. And then the framework is going to output the final values from the reduce function. So this basically, the user writes the map in the reduce function, and the library takes care of parallelizing all this computation across the input files and using resources efficiently. So the MapReduce, you submit a job to the scheduling system, which says I would like to use a few hundred CPUs or something. And so it starts up all these tasks. One of them is special. It's the MapReduce master. It's going to take care of dynamically load balancing the work that all the other workers do and telling them which piece of input data they should process next. And so that worker is going to read this piece of the input files and process it with the map function and produce a bunch of intermediate data that's going to be read by the reduce operations. And then eventually the reduce operations will kick in and read all the intermediate data that's appropriate for them, and then process it, apply the reduce function, and write the final output data. One very nice thing about this programming model is that failure recovery is startlingly easy. Because if a worker dies, you just re-execute what it did. And you do a bunch of bookkeeping to keep track of the fact of where the intermediate data is stored and so on. But it's actually pretty simple. You can actually also do things like when you're getting close to the end of your job, you spawn off 3 copies of each of the last little bit of work. And whichever one finishes first, well, that's the one that's going to win. And the other ones, well, you wasted a little bit of computational resources, but your job got finished faster. That's actually important for us because we often end up with kind of sluggish machines causing trouble, where if you have 1,000 machines, chances are they're not all actually going to be identical, even though the hardware is identical, because sometimes you end up with one that has a disk that's getting lots of soft errors, and so it'll read, but slowly, at like 1 megabyte a second instead of 20 megabytes a second. Or recently we had actually a bug in our BIOS that wasn't considering the fact that processors could be hyper-threaded. And so when you rebooted a machine, there would be a 2% chance that it would come up and with all the caches disabled, which was particularly annoying because you have a machine that works, it's just 100 times as slow. So multiple executions can actually take care of even issues like you have a bunch of cacherless machines sitting in there. And it's actually very robust. It's able to tolerate really large-scale failures. So for example, one time there was network maintenance being done on a job while a job was being run in this cluster. It was kind of a scheduling snafu. We didn't realize they were going to do maintenance. And we lost 1,800 of 2,000 workers, but the map production eventually finished just fine. So we've been pretty happy with how broadly applicable this fairly simple programming model has been. And we use it for all kinds of things. And we've actually rewritten our production indexing system completely using a bunch of map reductions. And it's much simpler than the old code, which had kind of intertwined a bunch of things about parallelizing the computation, about fault tolerance in each of the different phases, as opposed to leaving it up to the library. And you can see we've used it pretty heavily. This is some stats from some of the MapReduce usage in August. And the interesting thing, I think, is that there are 400 different kinds of map reduction operations run in that month. So it's pretty applicable. We have an upcoming paper in LSDI about it, which you can get a copy of there.
You lost 35,000 workers? Isn't that a dangerous place to work?
Yeah, that's why we're hiring. The other thing it does for you is it keeps pretty status pages, so you can kind of monitor your computation. The green area is the map work that's been assigned but is in process. The red area is data that's been shuffled to the reduce workers. So you can see that the reduce workers kind of keep shuffling as map work is being completed. The blue now is reduce work that is starting to be done and written, and you can kind of see over time. This particular job, we're using 1,707 workers. We've had a death, but who knows where? Doesn't matter. And this is actually one of our phases in our indexing system. And away we go, 38 minutes, 40 minutes, great. OK. So that's kind of a view of some of the systems infrastructure that we found useful to build over the past 2-3 years. And the whole reason for building this is because we have a lot of data that we want to process and make available in various services to allow people to search over. And so if you have a lot of data and a lot of CPUs that are easy to use, there's a bunch of interesting things that you can do. So I'm just going to highlight some of them. So one thing you might say is, well, I wonder how many queries we get for different for queries that contain different interesting words over time. So this is 6 different graphs over the same time period for each of them, from January 1st, 2002 until sort of mid-2003. So it's an 18-month period. This is December of 2002. So the first query is queries containing Eclipse. And you see there's always kind of a little background noise because of Mitsubishi, which makes a car called the Eclipse. But on 3 particular occasions, there was a huge spike in queries containing the word Eclipse. And so that's kind of cool. I like full moon, personally. Every 28 days, we get a big peak in how many queries we have containing the word full moon. Interestingly, there's no corresponding new moon thing shifted by 2 days, because no one can see it. If you look closely, you could probably figure out that that was a solar eclipse there, because it's right during the new moon, I believe. So the next one is watermelon, which has kind of a lull in the winter as watermelons are not available. And then a steady rise over the summer. And just before July 4th, there's a big peak in queries containing watermelon because people want to figure out what to do with their watermelon at their picnics. So we have queries containing World Series. And I did this, and I was expecting to see a big peak in October, and sure enough, there is. But there's 2 other peaks, which was kind of surprising to me until I thought a little bit more. Any guesses?
Poker World Series?
Little League.
World Series of Golf?
Poker.
Close. They're both baseball related. So one's the College World Series, and one's the Little League World Series. This one's kind of interesting, the Summer Olympics one, because it's 2002. Curious. Which was not during the Summer Olympics, but was during the Winter Olympics. So I guess this is people who are just kind of gymnastics starved and don't care about ice skating or something. And then you see interesting things when kind of new terms come into existence, where you didn't get any queries for Opteron, which is a processor that AMD makes now. And then they announced that they were going to be making this product called Opteron. You see a small flurry when they first announced it and some background stuff. And then they actually released the product, and there's a big spike and a fairly heavy increase in average volume. That's kind of cool. This is actually not input data. This is output data from our spelling correction system. So all of these are things that the spelling correction system corrects to Britney Spears. Well, actually, the very top one is a correct spelling of Britney Spears, which occurred 408,000 times or something over this interval, which I think was a few months long or something. And you see that actually misspellings are a pretty common problem in search queries. If you look at sort of query logs, you see roughly 10% of queries contain some sort of misspelling. So So this is actually a big quality problem for us, because if you have a misspelled query, what are you going to match? You're going to match documents with misspellings. Well, perhaps those aren't the highest quality documents in the world. And so you see, the most common misspelling of Britney Spears occurs 10% of the time that the correct spelling does. And there's a very long tail of this, various butcherings of Britney Spears' name. So that's kind of fun. Search engines today, basically, they take your query and they look for documents containing the words you typed in. And they rank them in some way, like trying to count if you have multiple occurrences of the word, that's good. If they're close together, that's kind of good. If they have query-independent things like PageRank, that's, higher PageRank documents are generally better than lower PageRank, things like that. But the real goal of what we're trying to do is when you type in a query, we want to find you the documents that are relevant to your query. And often those aren't necessarily the ones that have exactly the words that you typed in. So for example, the query Bay Area cooking classes, it would be nice if that matched these 3 hypothetical documents. So it should match the San Francisco College night class, Mexican cooking for everyone. So what would be involved in making it match that? Well, let's see. You'd need to know that San Francisco was in the Bay Area, assuming the user was referring to the San Francisco Bay Area, not Tampa Bay or something. You need to know that class is related to classes. It's a STEM. That's not too hard. And cooking's already there. So you need to know a little bit and do some stemming, and you could get the first one. The second one is a little bit harder. You need to know Stanford University is in the Bay Area. You need to know that courses are related to classes. They're basically synonyms. And you need to know that cuisine and cooking are also related. Right? So that one's a little more challenging. And then maybe this one, you have a page that says Berkeley courses and then has links to a bunch of pages about the courses, but the actual pages don't say courses on them anywhere. It's sort of implied by the link structure of the particular website. You'd like to perhaps flow information, look at information not just on that page, but in the neighborhood of that page. OK, so those sound like interesting problems. How are we going to solve those? So one thing about having lots of data is that you can do interesting things by processing the data and looking for interesting correlations between, say, one word and another. So what I'm going to show you now is a demo of a system that is trying to build clusters of words that it believes are related. It doesn't tell you how they're related. It just tells you that it thinks that if you're talking about this, these are a bunch of words that might be related to that particular topic or word. It's trained on a bunch of documents, and it's completely unsupervised. So it has a bunch of clusters, but the model started out by having no clusters at all. We didn't sort of precede it with a bunch of clusters and add words to the existing clusters. It's completely unsupervised. It used many CPU years in order to train this model, and we learned a model of about 500,000 clusters. Some of them are really small, few words. Some of them are huge, a few 100,000 words. And the names that I'm going to show you in the demo are named automatically for the 5 most prominent words in the cluster. OK, so is that big enough? A little bigger? OK. Better? OK. So this is the model of clusters. Each one of these lines represents a cluster. And if we click on them, like say this cluster, you'll see that the cluster contains actually, the model that we learn actually has connections between clusters. We tried to learn a hierarchical model of parents and children and the relationships between the clusters. And that kind of works sometimes, but is not as compelling as the actual contents of each cluster. So this cluster contains basically a bunch of first names, English first names. And it kind of goes on. Each word has a probability of being basically, if this cluster is something that seems relevant to your query, this is the probability that you would utter the word James when you pick a word at random out of the cluster. And this is in decreasing probability order. You can see it kind of goes on for a long time. we just change our UI when we get tired of showing details of ones. And then eventually we give up and we just say, well, there's 236,000 words in this cluster. So this is one of your larger clusters. And so that was names. There's, what's another interesting one? Let's look at cars. So, for example, here's words related to buying a car. Kind of cool. So this is just kind of the raw data that's in the model that was learned. So let's try typing in a query. Let's try cooking. So cooking. It says, when you type this in, it basically tries to infer what clusters it thinks are most likely to be relevant to the words you've typed in. And so it says with 46% probability, this cluster about recipes basically is on. And it explains 0.44 words in the query. And then there's some other clusters with decreasing probability that it thinks are on. So you can look at the recipes cluster. It's probably full of recipe words. Cooking, dessert, low fat, so on. Now this is kind of an interesting one, because you see that cooking and cuisine both appear, right? That's kind of cool, because that was one of the problems we had with the earlier documents, right? We wanted to know that cooking and cuisine were related in some way. Ideally, we'd like to know that they're synonyms, but this at least tells us there's a strong correlation between those two words. So if you're likely talking about cooking, there's a high chance you would utter the word cuisine. OK, let's see. How about classes? Classes, well, there's, courses. Look at that. Hey, cool. That's kind of neat. So the other thing this thing allows you to do is, suppose you type in the query rolling hash. Being a computer scientist, I know what I'm expecting. This is where personalization would really help. It should know that I like MD5s. But apparently, if you just type rolling hash, the most likely cluster for you is the top one, which is not about what I thought it would be about. OK, but interestingly, if I type rolling hash function, the system uses all the words in the query in order to determine what are the most likely clusters. And so just the addition of that single word has helped disambiguate the, well, perhaps it didn't seem actually that ambiguous before. It was pretty sure in the other camp. But just this has been enough to change the meaning of what the system thinks the likely clusters are over to the, I won't say more traditional interpretation, but so there's a bunch of words related to cryptography and MD5s and rolling hash functions. So that's kind of cool. Another thing that you can do is, let's try sort algorithms. So there's a cluster about sorting algorithms, which is kind of cool. You can imagine if someone types the query sort algorithms into Google, even if you match only documents containing the word sort and algorithms, you'd like to perhaps give a boost to pages that also contain these other terms. Like, say, quicksort would be a good one, right? Bubble sort, well, maybe not so much. But anyway, and here's a whole bunch of words related to sorting. Complexity, linear, implementation, data structure, sort, iterative, pivot, so on. So that's kind of fun. The other thing you can do is, let's pick a word, like, say, algorithms. So it tells you there are a bunch of clusters here. This is kind of a general algorithms cluster. Optimal search, efficiency, approximation, blah, blah, blah. You can also see what clusters a word occurs in. And we allow a word to be in many clusters. So here you can see those are sort of the most prominent clusters, sort of the most general ones. But then you get down to very specific clusters about compression algorithms, about recursive algorithms, randomized algorithms, wireless mobile algorithms, and so on. And there's a whole bunch of clusters, showing sort of the breadth of the different subjects that are represented here. And the sizes of the clusters are quite variable. So now I'm just going to kind of highlight some of the other interesting non-web search related things we've been working on and focus on what some of the interesting problems are inside those products. So Google News is something we launched, I forget, maybe a year and a half ago. It's basically a completely automatically generated newspaper that summarizes the news stories around the world. And the interesting thing it does is it takes, by crawling a bunch of news sites and collecting articles and then clustering articles together that are about the same story, you can get a fairly interesting user interface by allowing you to view different news organizations' coverage of the same issue. This is actually quite different than what most people do for news, which is they pick their favorite news site, CNN or New York Times or whatever, and they go there and they get that news organization's take on all the different articles in the world that day. Instead, this sort of allows you to pick an article and then look at the differences in coverage across different news organizations. And then we also automatically generate this headline page. You can search for particular news articles, but we also automatically generate news. Since it's news, you don't really know what to search for because that's why it's news. So you can sort of, with a little bit of classification into rough sections and some statistics about how large the clusters are, you can figure out what are the top stories in the day and what are the interesting stories in the world and the US and in science and so on.
How does it pick which one is shown on the front, like which of the various stories about the same issue?
You mean within the same cluster?
Yeah.
So how did it pick that particular Bloomberg story versus the?
Yeah.
There's a bunch of heuristics about how reputable is the news source, how fresh is the particular article that's being shown compared to the other articles in cluster and so on. So this is a product that we introduced about a year ago to allow small publishers to actually get relevant ads on their websites. Basically, the system works by examining a bunch of text. In this case, a web page, but it's applicable to anything. And then examining the advertising inventory that advertisers have given to Google to show on search result pages, and trying to find out which of those. Basically, the advertiser gives us a small textual ad like this. This is one ad. And then they've given us a bunch of words that they believe are relevant to their ad, or phrases. And so we essentially do a matching process where we try to match content of pages to contents of ads plus the keywords, and try to pick the most relevant ads. And it's actually a good experience for users of a site. Instead of kind of untargeted banner ads that say, maybe you want a Visa card, you get fairly relevant ads relevant to the kinds of information you're looking at. It's good for publishers because, let's face it, the Visa card ads don't get clicked on that much, whereas these do. And so they actually get more money to support their publishing. Google Print is a product we actually launched just 2 or 3 weeks ago, although we've had Google Catalogs, which allows search over catalog content. But Google Print is basically search over printed books. And the way this works is we take books and we chop them up. And then we scan them and run an OCR algorithm on them to identify the text. And then we provide search over the content there. And there are a bunch of interesting business issues about, how do you convince publishers this is a good thing? Will they actually sell more books or less books? But there's a bunch of interesting technical issues behind this as well, like how can you quickly scan lots of books? Do you have to chop them up, or are there ways to do it without chopping them up? Things like that. It's actually nice because the nice thing about book content as opposed to web content is that it's very high quality. It's been through a fair amount of effort goes into actually publishing a book. So writers tend to be more careful about the kinds of things they say than the effort involved in publishing a web page, which is lower. Another area that we've recently introduced a product is Google Desktop Search, which is basically a system for Windows computers that allows you to search files and other information stored on your desktop computer. And it's kind of integrated with our main Google search as well. All the searching of your local information is done on your local machine. We basically stick out a little funny tag in the web search results we send out, and then the local code proxies that and notices the little tag and then sticks in your local search results on that. So it's kind of seamlessly integrated with our web search. We index chats and web pages you've seen before, which is kind of handy. We have a bunch of other products. Probably Gmail's pretty well known. Basically, we're trying to provide a lot of storage for email and provide an interesting UI where we thread together messages in the same thread so that you actually see the whole conversation together. It's pretty nice. I've been using it for my internal email, which is good. I get a lot of email at work, so it helps me manage that. So now I'm going to talk a little bit about our engineering organization. One of the things we believe pretty strongly in is that you should hire people with who are really good at what they do and that are motivated to make their products or make whatever they're working on work well and solve interesting problems. And we also believe pretty strongly that working in small teams of people, like 3 to 5 people, is a really effective way of having people work together. If you get a lot bigger than that, you end up with these kind of weekly meetings where everyone says, oh, what did you do last week? And you end up doing this kind of n-squared communication of what everyone did last week. And you don't make as much progress on projects that you could if you had a sort of smaller, more focused team. And we also tend to try to focus on problems that sort of fit under our mission of taking interesting information and organizing it. I think the books thing is a very good example of taking information that's already available. You can go to your bookstore. But if you make it searchable in new and interesting ways, it will increase the value of that information a lot. And one of the things we focus on is everyone in our engineering group has 20% of their time to work on whatever interesting products or projects they have in their little heads. And they should feel free to play around with ideas. And from a lot of those ideas have come a lot of our interesting products, like Google News, AdSense for content, Gmail. All these things came out of people just kind of playing around on their own and sending out mail to people saying, oh, I have this interesting prototype or demo. Try this out. And people will get excited and send out ideas and suggestions for improvements and so on. The other thing I'd like to get across is that, and it's a fun place to work because you have lots of interesting infrastructure. Like you can actually get access to 1,000 machines to try out your idea, and which makes iteration of these ideas a lot faster and more pleasant. The other thing is it's not just sort of information retrieval that is sort of the core of what we do. We do interesting work across a very wide range of areas. And basically, there pretty much isn't an area of computer science that we're not doing some work in. And often it's the case that maybe we'll have someone working on the project who's really good at algorithms, and someone who's really good at machine learning, and someone who's good at distributed systems. And it's from these combinations of skills that a lot of the best products result. For example, the clustering algorithm was done by people really good at machine learning, and I gave them a tiny bit of advice on how to parallelize some of the computations. And from that, they were able to build more interesting and richer models. And so it's that kind of interaction that I think is really nice. And I'll conclude. This is an animation of 24 hours of queries where we've colored regions according to the number of queries we receive from that particular area. It'll take a little while, but you can see Europe kind of go to sleep just before the sun rises.
I think we ought to stop since Jeff's been up here for an hour. And let's thank him. And he'll be here afterwards, so if you want to ask questions afterwards, that's good. Okay. Thanks, guys.